Fuel cell, like internal combustion engine, is an energy conversion device. In this class we will see very briefly the working of fuel cell, what are the different types of fuel cell. However, when we studied the hydrogen production, at that time we have considered a similar device which is electrolyzer in much more detail. At that time we studied the thermodynamics of electrolysis process, the different components of electrolyzer and the different types of electrolyzer. The difference between an electrolyzer and fuel cell is that the electrolyzer takes electricity and water as input and produces hydrogen and oxygen, while fuel cell, that is opposite, it takes the oxygen and hydrogen as the input and produces water and electricity as the output. Just to give a brief background, the demonstration of a first gas voltaic battery was done by William Grove in 1839, when he proved that an electrochemical reaction between hydrogen and oxygen can produce electricity. So, that was the very first demonstration of a working of a fuel cell. It was later by Langer and Monde, they introduced the term fuel cell, and at that time they used coal as a fuel and obtained 20 amperes per meter square at a voltage of 0.73 volt. This cell they modified for a first time to make it into alkaline fuel cell. It was in 1950 when NASA first started developing fuel cell, and then they used it for the space missions. After that, since 1970s there was a lot of interest in fuel cell and especially for the vehicular application. Now when it comes to fuel cell, if we consider it to be a black box such that it takes hydrogen and oxygen as inputs and gives electricity and water as output. Now as long as we provide the fuel and oxidant, hydrogen and oxygen to it, it will keep on supplying electricity ideally. In that sense it works like a internal combustion engine. However, fuel cells, they are electrochemical devices which convert the chemical energy of fuel into electrical energy. As such, they have a similarity with the batteries. Both are electrochemical devices. But the major difference between fuel cell and battery is, in fuel cell if we supply fuel we will get electricity ideally continuously as long as we supply fuel, but in battery, and it is not being consumed, but in battery that energy, chemical energy is stored inside and then it gets used up. So that is the basic difference between fuel cell and battery. But both are electrochemical devices which convert the chemical energy into electrical energy. Now there is again a similarity with the IC engine. In IC engine it converts the chemical energy of the fuel into heat via reaction. Let us say hydrogen and oxygen, they combine to give water and heat. This is what occurs in the IC engine. So there is again similarity between fuel cell and IC engine, that it can be converted later on into mechanical energy and then into electrical energy, this heat being produced. Now what happens in case of an IC engine is, hydrogen oxygen reacting to produce water and heat. On a molecular scale there occurs collision between hydrogen and oxygen and that forms water. That is how it reacts. But on atomic scale what occurs in this particular reaction is, the hydrogen bond breaks, oxygen bonds these breaks, and the hydrogen oxygen bond is formed. So the hydrogen bond, oxygen bond break and hydrogen oxygen bond is formed. Now this bond reconfiguration, this occurs by means of an electron transfer. The bond configuration energy of the product is higher than the bond configuration energy of the reactants, and that difference in energy, it comes out as heat in the process. Now that means during the bonding reconfiguration, electron transfer takes place from one bonding state to another bonding state, and that electron transfer in this reaction which occurs in the internal combustion engine occurs in a matter of picoseconds and at subatomic scale. As such, this energy difference between the bonding configuration, that comes out only in the form of heat in case of an internal combustion engine. Now in this process, if this chemical energy in the case of internal combustion engine which is converted into heat, if that has to be converted into, so the chemical energy, if that has to be converted into heat, from there it has to be converted into mechanical energy and then finally electrical energy. That means the number of steps involved to convert chemical energy into electrical energy in case of an internal combustion engine is higher, and as such the process gets complex and inefficient because there will be losses involved at every step. Now this electron transfer that occurs at a time scale of picoseconds at subatomic scale, that cannot be harnessed or are difficult to harness. However, if that electron transfer which occurs during bonding reconfiguration could be harnessed, then we can directly convert this chemical energy into electrical energy, and that is what happens in a fuel cell. So this is what happens in a fuel cell. Now how such a less time scale that reaction is occurring at the time scale of picoseconds and on a subatomic scale, how these electrons can be harnessed. Now this can be done by spatially separating hydrogen and oxygen. So if these reactants hydrogen and oxygen, these are spatially separated, then the electron transfer will occur over a spatially extended length, and in that process when it is being transferred from one reactant to another, we can harness those electrons. And this separation, spatial separation, is done by using electrolyte. So this electrolyte spatially separates the two reactions which occurs in the fuel cell. Hydrogen forms H plus ions and 2 electrons are liberated, and these 2 H plus ions combine with oxygen and 2 electrons to give H2O. So the reactants are separated spatially by means of an electrolyte, and these two half cell reactions occurs at electrode's surface. So overall if we see, a fuel cell is an electrochemical device which directly converts the chemical energy into electrical energy, and the reaction is that the fuel with oxidant, it converts into electricity, certain amount of waste heat will be liberated and water as the output. Now this reaction that I have written here is for an hydrogen oxygen fuel cell, but then there can be other fuels also that can be used in a fuel cell, that we will see later. Now if we compare fuel cell, battery or IC engine, we see that there are certain similarities. Like in case of internal combustion engine and fuel cell, as long as you supply the fuel, ideally it should give the output. That way it is similar to IC engines. It is an electrochemical device, and as such it converts chemical energy into electrical energy. It has a similarity with the batteries. But then there are certain advantages of both batteries and internal combustion engines which are there in the fuel cell. So if we compare, then fuel cells, since they are directly converting chemical energy into electrical energy, they are more efficient than the combustion engines because the number of steps involved are less compared to that in the combustion engines. At the same time, the biggest advantage of fuel cell as against the battery is there is an independent scaling up that can be done for power and capacity. So we can have a higher fuel cell size or we can have a higher fuel reservoir. so as to increase the power and energy. So independently we can scale them up, and it is easier to scale up compared to the batteries. At the same time, these devices, electrochemical devices, fuel cell, they are more reliable, long lasting, since they do not have any moving part. As such, the operation is silent. At the same time, since the product is water and electricity we are getting as output, so there is no undesirable product which we are getting like NOx or SOx or any particulate matter. So these are basically the advantages of fuel cell, but then there are certain disadvantages also associated with fuel cell. They have higher cost, and we will see that the cost is higher because of the electrolyte or the precious metals at times which are used as catalyst, electrocatalyst. There is a limitation. So in fact battery and IC engines, they outperform in terms of volumetric power density. So power density is limited for fuel cell. At the same time, fuel availability and storage issues are there, these are the major challenges. And if we are using alternate fuels other than hydrogen, pure hydrogen, in that case we have to, those fuels have to undergo reforming, there will be auxiliary equipments, and overall the performance of fuel cell will come down. We use different catalysts. At times impurities present in the gaseous fuel, that also can cause poisoning of the catalyst. And then the dynamic conditions, the start stop cycling, that also need to be considered here, and that could be like there could be degradation associated with the start stop cycling. Now if we look at the basic principle of operation of a fuel cell in general, in fuel cell the current which is being produced, that directly depends upon the reaction surface area or the interfacial area. Now this is the area where electrode, electrolyte and reactants they meet. Now that means if we want to scale it up, if we want to increase the current being produced from a fuel cell, we have to increase that reaction area, interfacial area, and that is done in a fuel cell by making it thin and planar in structure. And at the same time we can have porous electrodes, not only to increase the surface area, surface to volume ratio, but also it makes the gas access easier in the fuel cell. Now if we see the basic operation of a fuel cell, then there are primarily 4 steps involved in its operation. First, the reactants, they have to be supplied to the fuel cell. Reactants are hydrogen and oxygen or hydrogen and air or the fuel and oxidant in general, because that will depend upon which type of fuel cell we are talking about. So there is a requirement of continuous supply of the reactants so as to get a continuous supply of the electrical output, and when it operates under higher current conditions at a higher rating, in that case that supply needs to be even higher. Now in order to have a continuous supply of fuel across, or fuel and oxidant or the gases on the 2 sides of the fuel cell, the flow field plates and even porous electrodes, they help in transport of the gases. Now these flow field plates, which are component of a fuel cell, they have channels or grooves such that it transport gases throughout the surface of the fuel cell. Now important is the size, the shape, the design of these patterns, these grooves, these channels and these flow field plates, that determines the performance of the fuel cell. Now second step involved is the electrochemical reaction, the 2 electrochemical half cell reactions. Now the current generated, we know that it is directly proportional to the rate of these electrochemical reactions that will occur on the anode and cathode side. And if we want a higher current output, so as such that rate of reaction or electrochemical reaction should be faster, and as such there is a requirement of catalyst to accelerate the reaction. Now appropriate choice of catalyst is essential together with the design of the fuel cell. Design of the reaction surface area is essential for getting a better performance of the fuel cell. Now the third step involved is conduction of ion through the electrolyte, and electron conduction through the external circuit. Now as mentioned, electrolyte it spatially separates the two electrochemical half cell reactions or the two electrodes, and it separates the two reactants in such a manner that ions which are formed on one side, these are transported through the electrolyte and consumed on the other side of the fuel cell or other electrode of the fuel cell. And similarly the electrons they are produced from electrode, they have to move through the external circuit to the other electrode and there they are consumed. So the electrolyte which is selected, as we have seen earlier also in electrolyzer, the electrolyte used is such that it allows the conduction of ions but not of electrons. So ion conduction should take place through electrolyte and electron conduction should occur through the external circuit. Now this ion conduction is however more difficult compared to the electron conduction, because these ions are more massive and larger in size compared to that of electron, and as such its transport is comparatively less efficient than electronic conduction, and this also gives rise to different losses. So it contributes towards the resistance losses. To address this issue, the electrolyte is made thin and that reduces the path for ion flow, ion transport across the electrolyte. The last step involved is removal of the product as they are formed from the fuel cell. Now this is an important step. The requirements are similar to what that was for the reactant delivery, and the products formed need to be removed, else the new fuel and oxidant will not be able to reach the reaction surface. And this is done in a similar manner as the reactant delivery is being done. Water flooding could be an issue in the fuel cell that needs to be considered. Just to revise some of the thermodynamic equations, we have also seen that in the electrolyzer, we know that the electrical work done by the charge is given by potential difference times the charge. So the work done is potential difference times the charge, W is equal to EQ, where Q is the charge, that is N times number of electrons transferred times the Faraday's constant. Now the maximum electrical work, it is minus delta G, that is the negative of the Gibbs free energy at a constant temperature and pressure, and this change in the Gibbs free energy is given by, if we substitute, then it is minus NEF. Now if we consider a hydrogen oxygen fuel cell, under standard conditions the value of delta G is minus 237 kilojoule per mole. So the standard state reversible cell voltage we can obtain by from here delta G upon NF, and that is given by 1.23 volt. So this is the reversible cell voltage under standard state conditions, atmospheric pressure, room temperature, and considering unit activities of the different species. Now in order to find the efficiency of a fuel cell, there is a thermal efficiency which is given by the useful energy divided by the delta H enthalpy change of the reaction, and the ideal efficiency is delta G upon delta H. Substituting the values under standard state conditions, 237.1 for delta G, 285.8 for delta H, we get the ideal efficiency to be 0.83 or 83%. And thermal efficiency can be obtained by useful power divided by delta H, which is delta G divided by 0.83, and that is 0.83 times the actual cell voltage divided by the ideal cell voltage. And ideal cell voltage we have just now seen, it is 1.23 or exactly 1.229 volt, which can give us the voltage efficiency to be 0.83 times the actual cell voltage divided by the ideal cell voltage 1.229, that is 0.675 times the actual cell voltage, which will give us the voltage efficiency of the fuel cell. Or the net cell efficiency could be obtained as voltage efficiency times the fuel utilization factor. So this is very briefly we have talked about some of the relations used in the fuel cell. Now there are different types of fuel cell depending upon what electrolyte it is being used. The fuel cells can be, as we have seen on electrolyzers also, fuel cells also can be categorized into different types, like the proton exchange membrane fuel cell, molten carbonate fuel cell, alkaline fuel cell, phosphoric acid fuel cell, and solid oxide fuel cells. Now let us consider first the polymer electrolyte membrane fuel cell. This is the fuel cell which has highest power density as compared to the other types of fuel cells that we are going to consider, and the name itself suggests it is polymer electrolyte membrane or proton conducting membrane which is used as an electrolyte. The most commonly used membrane is Nafion, and that membrane, it has to be operated at temperatures because we are using a membrane that has to be hydrated to maintain the conductivity. It cannot operate beyond 90 degrees centigrade. The electrocatalysts used are platinum, and these are coated on either side with platinum based catalyst and porous carbon electrode support material. The combination of electrode, catalyst, then membrane and the other side catalyst electrode structure, this combined structure is known as membrane electrode assembly. So since they operate at less than 90 degrees centigrade, so the low temperature operation of polymer electrolyte membrane fuel cells, because of that they can be used for various portable application. In general, the reaction that occurs on the anode side is the hydrogen forms proton and 4 electrons here, 2H2 giving 4H plus 4 electrons. These electrons flow through the external circuit, protons are conducted through the electrolyte, the polymer membrane. It goes on to the cathode side where it reacts with the oxygen plus 4H plus 4 electrons giving 2H2O. So the overall reaction is 2H2 plus O2 giving 2H2O plus electrical energy and heat. Another category of fuel cell is alkaline fuel cell. This was for the first time used in Apollo mission by NASA, and this can be operated in a wide temperature range. As the name itself suggests, it is an alkaline electrolyte. Low cost KOH is used as electrolyte in such fuel cells, and the biggest advantage of alkaline fuel cell is they can use non-noble metal catalyst which reduces the cost, and they have a lesser crossover problems compared to the polymer electrolyte membrane fuel cell. They can produce current density which are similar to PEM fuel cell, and the reaction that takes place is 2H2 plus 4OH minus. So the electrolyte is an OH minus conducting electrolyte. So 2H2 plus 4OH minus giving 4H2O plus 4 electrons, this flow through the external circuit. This 4OH minus moves from the or is migrated from the electrolyte through the electrolyte to the cathode side reacting with oxygen, O2 plus 2H2O plus 4 electron giving 4OH minus. The overall reaction is 2H2 plus O2 giving 2H2O plus electrical energy plus heat. The next class of fuel cell is phosphoric acid fuel cell. Now in this H3PO4 is used as the electrolyte, and either a dilute or a highly concentrated phosphoric acid is used as an electrolyte. This was the first commercial fuel cell which was used for stationary applications, and the components which are used, because we are using an acidic electrolyte, so it is essential that the components which are used needs to be acid resistant. It is tolerant to carbon monoxide, it can be 1.5% that is tolerated, and as such that provides a flexibility towards the choice of fuel. Sulfur here needs to be removed. The major disadvantage associated with phosphoric acid fuel cell is they have a low efficiency and high weight. So the reaction that occurs on the anode side is 2H2 giving 4H plus 4 electron. These 4H plus they migrate onto the cathode side and electrons to the external circuit. On the cathode side the reaction that occurs is O2 plus 4H plus 4 electron giving 2H2O. So the overall reaction H2 plus O2 giving water plus electrical energy and heat. Molten carbonate fuel cell, the name itself suggests they are high temperature fuel cell. The electrolyte is made up of molten carbonate salts and they require carbon dioxide at cathode. So it is produced and consumed within the fuel cell, and since this is a high temperature fuel cell, there are issues associated with the stability of the material. They are more resistant to impurities compared to the other types of fuel cell, but the major challenge is their short life and high cost. At the anode side, 2H2 it combines with the carbonate ion plus 2 CO3 2 minus giving H2O plus CO2 plus 4 electrons, and the overall reaction is 2H2 plus O2 giving 2H2O plus electrical energy and heat. Solid oxide fuel cell, they are again high operating temperature fuel cell, and it has fuel flexibility. We can use a wide variety of fuels for the solid oxide fuel cell, and name itself suggests that a solid electrolyte is being used, and here the issues related to managing the liquids as against the other fuel cells is not there. Now the solid electrolyte, it reduces the electrolyte thickness and it produces high quality byproduct heat that can also be used for cogeneration. But the major disadvantage that remains with solid oxide fuel cell is they are high temperature fuel cells, as such the material degradation at high temperatures is the major challenge, and need to have a lower cost of ceramic materials which are stable under these conditions is the basic requirement. If we compare the different types of fuel cell, then the operating temperature range, it varies between 40 to 80 for PEM fuel cell. For alkaline it is 65 to 220 degrees centigrade, for phosphoric acid 205 degrees centigrade, for molten carbonate 650, for solid oxide it is 600 to 1000 degrees centigrade. Electrolyte in case of PEM is a polymeric ion exchange membrane, usually Nafion. For alkaline it is mobilized or immobilized potassium hydroxide in asbestos matrix. For phosphoric acid it is phosphoric acid in silicon carbide matrix. For molten carbonate it is liquid molten carbonate in LiAlO2. While for solid oxides these electrolyte are perovskite based materials. Electrode is carbon based in polymer electrolyte membrane fuel cell, in alkaline it is platinum, in phosphoric acid it is carbon, in molten carbonate it is nickel and nickel oxide based, and here it is perovskite based in SOFCs. The catalyst which is used is generally platinum except for molten carbonate and solid oxide fuel cells. The charge carrier, depending upon the charge carrier or the ions which are transported, polymer electrolyte membrane they have H plus ion conducting membrane, alkaline fuel cell OH minus, phosphoric acid H plus, molten carbonate carbonate ion and oxide ion in case of solid oxide. Polymer electrolyte membrane usually for hydrogen as a fuel, but it is also can be used with methanol, then reforming will be required, alkaline with for hydrogen, phosphoric acid for hydrogen, and molten carbonate again can use hydrogen methane, and there is a wide fuel flexibility for solid oxide fuel cells. Now the major component, if we look at the polymer electrolyte membrane fuel cell, then the major component in a polymer electrolyte membrane fuel cell is the membrane electrode assembly, which consists of electrolyte membrane, that is a polymer which allows ion conduction. Then there is a catalyst layer. On the anode side, the catalyst, it allows hydrogen molecules to split into protons and electrons, and on the cathode side it reacts, these ions they react with the oxygen and then forming water. Then there are gas diffusion layer, we have seen their roles already. There are bipolar plates which provide electrical connection between cell and also provide strength to the cell stack, and gasket provides the air tightness. In a typical fuel cell, the standard reversible voltage we have seen is 1.23 volt, but then there are irreversibilities involved in the fuel cell. Now if we see the power which is being produced by a fuel cell stack, it is given by current density times the geometric area times the voltage. Now this voltage from the fuel cell stack is given by the number of cells operating in the stack times the voltage from each of the stack, and the output voltage of a fuel cell is given by the difference of the reversible cell voltage minus the irreversible losses. Now these irreversible losses, these can arise because of several reasons. One is because of the electrochemical reaction, their rate of the reaction, which gives rise to activation over voltage, because there is a resistance to the flow of ions and electrons, that gives rise to ohmic over voltage, and then there are mass transfer limitations which gives rise to the concentration over voltage. So if we consider the performance of a PEM fuel cell, we can plot cell voltage with the current density. So the actual output voltage is given by the ideal voltage minus the different sum of the different over voltages. So if we see in the lower current density regime, activation losses predominate. In the real operational region, ohmic losses these predominate in the medium current densities, and in the higher current density regime, mass transport losses are the predominant losses involved. There are different parameters which affect the performance of a fuel cell, like the current density. We have seen that the losses, they are directly proportional to the current density, and ohmic losses, they are usually dominate in the normal operation region of the fuel cell. If we want high current density or high power density, that will also result into a lower efficiency. It also depends upon temperature. So, the losses, they decline exponentially with the increase in temperature. Impact of temperature on cell resistance, it varies with the material. For aqueous electrolyte, the high temperature leads to membrane dehydration and it also leads to loss of conductivity. Mass transport losses, however, they are not affected by the temperature. The another important parameter which affects the performance of a fuel cell is pressure. If there is an increase in the operating pressure, it has several benefits. The gas solubility, mass transfer rates, they increase with pressure. The electrolyte loss by evaporation also reduces, but the disadvantage is if we increase the pressure, then the piping thickness will increase, we have to pressurize it, and that will add up to the cost. And gas composition also affects the performance. The change in the gas composition, it cause reduction in the cell voltage. So, that could be the relationship we can get by the Nernst equation. There has been several developments recently. Fuel cell has been considered to be a major component which could be helpful towards green energy transition. There are certain key market players, companies which are in the key player in the fuel cell development, like the Ballard, Fuel Cell Energy, Mitsubishi, Plug Power and Cummins. Fuel cells, they are widely being explored for their use for distributed power as well as vehicular application, and they have a wide range of application, wide scope of application in automobiles that could provide the longer driving range and lesser fueling time. Asia Pacific has emerged as a major market for fuel cell because of the policies, government policies like in countries like China, Japan, South Korea, where the interest in fuel cell has increased, and major applications being considered is heavy duty transport and energy storage. In 2020, South Korea surpassed the United States and China and gained a leading market in fuel cell electric vehicles, about more than 10,000 vehicles in South Korea. In 2021, Toyota, they unveiled a new hydrogen production facility and gas refueling station at its factory in Melbourne, Australia. And in December 2021, Hyzon Motors, they announced the delivery of 29 fuel cell electric trucks that will be used in China in a major steel conglomerate. In 21, Edison Motors, they signed an agreement with Plug Power for providing to develop and market a hydrogen fuel powered electric city bus. And as per IEA's global EV outlook, China accounts for 94% of the fuel cell buses and 99% of the fuel cell trucks. To summarize, we have seen the electrochemical device fuel cell which converts chemical energy into electrical energy. It is a very efficient, reliable, scalable device which does not produce any pollutant. There are different types of fuel cell we have seen very briefly, and when it comes to the economies of scale will be the major contributing factor which will bring down the cost of fuel cell. Thank you.